Welcome to Data Mining, Lecture 5, Part 2. The subject we will discuss today is clustering, and this will conclude the clustering part, and this will basically finish all the materials regarding clustering. As I said many times, this subject is still a research subject, meaning that there's no boundary for this. So we talk about clustering today. We spent 2 lectures in clustering, and basically this is just an overview or introduction to clustering. Okay, the clustering itself is much larger. It's a much larger research field where you can find a lot of interesting and useful ideas. Okay. Last time, we talked about one particular clustering algorithm, which is the k-means algorithm, which is a partition-based clustering algorithm. By partitioning-based clustering algorithms, we mean that those algorithms keep on partitioning the data objects or data points in such a way that through many iterations, eventually at one point, data objects can be partitioned very well so that similar objects can be put in the same group. And like every other clustering algorithms, the k-means algorithm needs a user-specified parameter value, k, which represents the number of resulting clusters the user expects to see. As we pointed out last time, and also as one of the students mentioned in this class, how do we know what k is best in advance? How do we know which k we should input so that the algorithm can give us good k clusters, right? It might be the case that data themselves are in 3 clusters while the user specifies that he or she wants 2 clusters only. For that case, there will be some not matched or unfitted data. You are right, okay? So there are a lot of improvements to try to improve the classical k-means algorithm so that it can work better in practice. Similarly, for today's algorithm, which is the agglomerative algorithm, there are a lot of improvements over this classical algorithm I'm teaching here so that the algorithm can work better. Okay. If you are interested, I would like you to look at my web page, go to the publication page, and click on the paper we published in year 2000 on the journal Knowledge and Information Systems. The title of that paper is An Index Structure for Data Mining and Clustering. Download that paper, you read that paper, you can find a lot of references about improvements on clustering. Okay, so that's basically will give you one pointer regarding better clustering strategies. So this algorithm I'm talking about here today is by no means an optimal algorithm. This just give you a rough idea about how a hierarchical clustering method can work. So the agglomerative algorithm is one hierarchical clustering method, and there are many other hierarchical clustering methods available in the literature. What is a hierarchical clustering method? Or specifically, how this agglomerative algorithm can work? Let us look at this algorithm step by step. Initially, we treat each object as a cluster. So suppose you are given 100 objects. So initially, you start with 100 clusters. Okay? And then you merge 2 clusters that are closest. You merge 2 nearest clusters. That's step 2. So after step 2, supposing initially you have 100 clusters. After step 2, you are left with 99 clusters, because in the step 2, you merge two nearest clusters together, and they become one cluster. So this is like a hierarchical way where you organize the data. You start with 100 clusters, okay? Then you merge two nearest clusters into one cluster. So now you have 99 clusters. You do similar things through the iteration. Then you find another two nearest clusters. You merge them together so that they become one cluster. So after this step, you are left with 98 clusters. You keep on doing so. 97 clusters, 96 clusters, and so on and so on. Now suppose you specify that you want to have 2 clusters only. So you keep on doing so, and at the end, you are left with 2 big clusters. And this is like a hierarchy, right? You start with a base where you have 100 clusters. You keep on merging nearest clusters, and you have few clusters where each cluster becomes larger and larger, right? So now eventually you are left with only 2 clusters. So that's why we refer to this clustering method as a hierarchical clustering method, because you start with many clusters while eventually you end up with 2 or 3 clusters, which gives you the result. So this is a hierarchical clustering algorithm. In contrast, in the k-means algorithm, that algorithm keeps on partitioning data. Okay, so they work fundamentally different, in a fundamentally different way. Okay, and that algorithm belongs to the partitioning method, and there are a lot of partitioning clustering algorithms. The k-means algorithm is just one of them. Similarly, there are a lot of hierarchical clustering methods, and the agglomerative algorithm is just one of them. Okay, now the idea is that, okay, at the step 2, you merge 2 clusters that are closest to each other. You merge them together. How do you measure the distance between clusters? Okay. If you download my paper on the web, which was published in the year 2000 on the journal Knowledge and Information Systems, you can find a way to define the similarities of clusters. Here is another way, which is a very simple way. Now, suppose you have 2 clusters. In general, this cluster might have 10 objects. This cluster might have 5 objects in general, all right? How to find the distance between these 2 clusters? Well, what we do is we find the distance between one object from this cluster and one object from this cluster, right? And we can find them all such distances between one object from this cluster and one object from this cluster. Suppose you have 10 objects in this cluster, you have 5 objects in this cluster. Totally, you calculate how many distances for all these combinations of object distances. How many? 10, 5. So that would be 10 times 5, right? Right, you choose this, and then so you have so many different distance values. Then you find the smallest distance value between an object here and an object in this cluster. And that smallest distance defines the distance between these 2 big clusters. That's how we define the distance between clusters. You see my point or not? In other words, to find the distance between 2 clusters, you calculate the distance between one object here and one object here. And you do this calculation for each possible object in these 2 clusters. So suppose you have 10. For the first object, you find the distance between that object and all the 5 objects here. For the second object, you find the distance between this and every object here, and so on and so on. So now you have 50 distance values, right? And then look at this distance value, you find the smallest number. That gives you distance between these 2 clusters. Any question about the way we calculate the distance between clusters? Then how to calculate the distance between objects? As I said the last time, that's another big research topic. Suppose these objects are points in Euclidean space, then the distance could be just Euclidean distance. But if the object is a graph, then how to calculate the distance between 2 graphs is a research area. Now, once again, if you are interested, you look at my paper on my webpage. I have several papers in calculating distance between graphs and so on. The first paper was published in 1995, Algorithms for Approximate Graph Matching, in which I have defined the distance between graphs. But that's my definition. There could be many other definitions between graphs, and for each definition, you can develop different algorithms to find that distance or to calculate that distance. Okay, so that gives you an idea about how to calculate distances between data objects. The distance between data objects depends on what data objects you are looking at and how you want to measure that distance. Okay, the simplest way is use Minkowski distance we talked about last time. Okay, or to use the space-specific Euclidean distance, or use other type of distances. And then, so that gives you these basic step, and you repeat this step until a user-specified condition is met. For example, until K clusters are obtained, where K is given by you. Now, so this parameter value then becomes important. How do I know what K I should specify beforehand? How do I know how many clusters I eventually want for these data points at hand? We don't know. So sometimes people use try and error. I use specify K being equal to 2. I do clustering, and I look at the result. They are not satisfactory. Then I try K being equal to 3, and recluster again, and so on, until I see that I obtain very satisfactory clusters. Okay, but there are many other heuristics that can help to improve this agglomerative algorithm. Any question about how this algorithm works? So let us move on to a specific example. Examples always help us to understand how the algorithm works. Suppose you are given this 10 data points or data objects. And suppose these data points are points on a two-dimensional Euclidean space. So each data point has x coordinate and a y coordinate. For example, if you look at this point, the x coordinate is 5. The y coordinate is 9. If you look at this point, the x coordinate is also 5. The y coordinate is 16, right? So you can find the x coordinate and the y coordinate for each data point you have in your database. And we use the Euclidean distance to measure the distance between any two data points, because everybody understands the Euclidean distance. We all learn the Euclidean distance from the high school. So we use that simple distance measure to illustrate how the agglomerative algorithm works. Okay? So we start with these 10 points. And initially, each data point is one cluster. So now you have 10 clusters. And your goal is to eventually come up with 2 clusters only. So you start with 10 clusters. You want to merge, you want to keep on merging them until you have only 2 clusters at hand. Okay? And intuitively, what you do is to put similar objects in one cluster and put these similar objects in separate clusters. That's the whole point of clustering. Okay? At the end, you want similar objects to be grouped together, and those objects that don't look like each other, they will be in separate places or in separate clusters. So initially, you start with 10 clusters. Okay? So you try to find the nearest clusters. To find the nearest clusters, you have to calculate the distance between these clusters. You have, for given 2 clusters, you have to calculate their distance. And as I said the last time, how to calculate the distance between 2 clusters? You look at the points inside those clusters and find 2 nearest points. And then their distance gives the distance between their respective clusters. Okay? So these 2 seem to be pretty close. So I calculate their distance. Well, in general, of course, you can calculate all the pairwise distances. Well, in fact, all the pairwise distances can be pre-calculated already. They are there already, so that you don't need to recalculate every time. You see my point? That's an optimization. You can just pre-calculate these pairwise distances. For any 2 objects, you have their distance value. You put that in an array. And so that every time you can just look at that array and you can get the value. Is that clear to you? So look at the array, you see the distance value between these two data points. You see the distance between these two data points. This is distance A, this is distance B, and this is distance C. These three, A, B, C, are the most likely smallest distance values among all the pairwise distances. Okay? So for illustration purposes, I just focus on the three, and then I calculate their values. A is 2.83, B is 3.16, C is 3, A, B, C. Which one gives you the smallest number? A is smallest, meaning that these two data points are closest. Therefore, these two clusters are closest because right now each cluster has only one data point. Okay, so we should merge these two clusters. Our algorithm tells us that we should merge two nearest clusters at each step in each iteration, right? So in this iteration, I merge these two clusters. So you see, so now at the end of this iteration, I end up with 9 clusters in which these two clusters are now merged into a bigger cluster. And I use a bigger circle to represent that bigger cluster. Any question at this phase? Then you go to the iteration again. This is an iterative algorithm, iterative program, you know. So once again, you try to find two nearest clusters. Okay? So because we have all the pairwise distances pre-calculated, all these distance values are there. So I can just look at these distances. I can sort those distances so that I can know who is the smallest, which number is smallest, which number is biggest. And so you always can do some heuristics when you are developing a program. So these two seem to be pretty close, and their distance value is A. This distance value is B. This distance value is C. So I look at A, B, C. Okay? Now, of course, in general, you also look at the other distance value. Look at these two. This distance is also pre-calculated, but it's too far. So you know that that won't be a candidate. You should not consider that, you know. You only try to merge nearest clusters. You know, these are possible nearest clusters, A, B, C. So you calculate distance values. A is 3, B is 3.16, C is 4. Now, these are Euclidean distance values. It's not difficult at all for us to calculate, right? x1 minus x2 squared plus y1 minus y2 squared, and you take the square root. That gives you the distance values. So A is the smallest. So we should merge the two nearest clusters. So I merge these two nearest clusters because the distance value is smallest. So at the end of this iteration, I'm left with 8 clusters only. Okay? Then I go to the iteration, the beginning of iteration again, go to the next iteration, try to find the two nearest clusters and merge them together. I keep on doing this until I come up with only 2 clusters. Okay? So for this, right now I have 8 clusters. Now I just try to find some close clusters. So I calculate distance. This is distance value A, distance value B, distance value C, A, B, C. And I calculate the distance values. And A is the smallest. Okay? Now, notice here that the distance between these two clusters that I'm pointing out right now, can you see this clearly? The distance between these two clusters is defined as the distance between these two data points. As I said already, right? The distance between these two clusters is the smallest value between the distance between these two data points and the distance between these two data points. It turns out that this has the smallest value. So that distance value is used as the distance between these two corresponding clusters. That's how I calculate the distance between clusters. I use the distance between data points to calculate the distance between the corresponding clusters. Any question? So these two clusters are nearest among these current data clusters. So I merge them together. Okay, so now I have 7 clusters right now, and I keep on trying to merge 2 closest clusters. Any question? So this is pretty simple, right? Now again, I try to find some candidates. Distance at value A here. Distance value B here. Distance value C here. And then we calculate the values. And it turns out that A is smallest. Okay? 4, 4.24, 4.12. So this is smallest. So you should merge them together. Okay? So I merge them together. So now at the end of this iteration, I have only 6 clusters. Any question? Actually, we have applied this clustering algorithm to cluster protein data, protein 3-dimensional protein structures, and for the for some cases, this algorithm works very well. The key thing is depending on how we define this distance between proteins. What we do is we use some motifs or amino acids or residues discovered from these 3-dimensional protein structures. We discover some frequently occurring residues from proteins using our tool, and then we use those residues, and we represent them as character strings, and we use Hamming distance to define this character strings, and then we can find the distance between 2 protein 3-dimensional protein structures. And once we have the distance between 3-dimensional protein structures, we apply this hierarchical clustering algorithm to try to cluster proteins. So actually the idea is how you calculate the distance between proteins. Now once you can calculate the distance between proteins, you can just plug in this algorithm easily. So that gives you an application of this clustering algorithm. Does that make sense, Jimmy? That makes sense, right? For those of you who are interested in reading that paper, you go to my website. This paper was published in 1998 on the ACM SIGA KDD Data Mining and Knowledge Discovery Conference. The title is Automated Discovery of Active Motifs in 3-dimensional Proteins. And you can find how you can find our methods and applications to try to do the clustering in the protein area, in the bioinformatics. What we do is we develop basic framework or basic algorithms, and then we find the applications. We apply this to bioinformatics, we apply this to XML, we apply this to web. If you look at the book, Web Data Mining, that's basically the survey we have written. Before you want to do application, you have to survey what's going on. So we write a book to do that survey. Right now, we try to look at XML. Then again, we write a survey to know what happens right now, and we get into there. So we will present our survey paper in the Principal Database Conference. You look at my book, 1999, Pattern Discovery in Biomolecule Data. That one is considered as the first one ever in the data mining bioinformatics area. Because of that book, it becomes known in this field. Because we published the first book through the Oxford University Press. And Oxford University Press has published a lot of most prestigious biological journals in their field. So through this bioinformatics book, basically they promote this book in the biological field. So suddenly people in the biological field understand that there's another bioinformatics group and in the world, The nucleases research and the bioinformatics journal, many journals are published by Oxford University Press. So we publish a book through that channel, and in that book, what we do is we survey what happens before 1998 about bioinformatics data mining, and we invite those authors who are leaders in that field to contribute a chapter to talk about what they believe about bioinformatics and data mining, what they think how they define bioinformatics, data mining, and so on. So we invite them to give the talk, to give a paper, and so on. So that's how we do the research, okay? So last time you asked me about applications. Applications are everywhere. The point is you have to look into them. Applications are not presented to you automatically. What you learn is a basic framework, okay? In the class, we cannot give you too many applications because of time constraint. We give you the basic framework, and then later on you find other applications on your own. Just like right now, we are also finding applications about our research. We have to convince this National Science Foundation who funds our project, where are our applications, whether this research is meaningless, useless, or the research has a lot of applications, has a broad impact to the community. So you look at this algorithm, very simple algorithm. You do the step-by-step and you do the iteration. Use the Euclidean distance. Yes, you are right. But these are for illustration purposes. Because all of you know the Euclidean distance. So I started with the Euclidean distance. There are many other distance measures that are much more sophisticated than Euclidean distance. By just talking about one particular algorithm, we have to spend 2 lectures, 2 different classes to only cover one algorithm, calculating the distance for between 2 data objects. So if we spend more time doing that, then we have less time to cover the fundamental frameworks or these ideas about clustering, which is a core in the data mining. You see my point or not? So that's why we can only discuss this basic methodology, while we give you room for your research so that you can develop your own methods, or you find the methods to calculate distances. Once you change the distance between data objects, the whole thing becomes different. You change your data points to proteins. You need a distance between proteins. That's one technique, by the way. Another approach is that, as our MetriMap does, or FastMap does, is to map proteins into Euclidean points. You do either way. You see my point? You want to cluster proteins or your protein structures or protein sequences. You have 2 strategies. One strategy is you develop a distance between protein sequences, or you develop a distance measure for DNA sequences. And there are a lot of such distance measures published in the literature. If you are interested, I can give you pointers, okay, to those papers. Many papers were published talking about how to measure the similarities between distances. They use alignment or scored alignment and so on. A lot of people at the NIH are doing with this. Protein structures. Jimmy is working in the PDB. A lot of people are, dealing with finding similarities between protein structures. So you can just take those similarity measures and then use this hierarchical clustering algorithm or the previous k-means clustering algorithm to cluster them, and then to verify with the real protein cluster to see whether they are consistent or not. One is done by lab. This is done by computer programs. You can check to see whether they are consistent or not. That's the whole point of bioinformatics, using the computer programs and tools to come up with these results to be verified with lab experiments, or vice versa. Lab experiments are verified against the bioinformatics results. So one strategy is to get those similarities between protein or DNA or RNA sequences, and then apply these distances to clustering them using the, for example, agglomerative algorithm. Another strategy which was very interesting, which was pioneered by Christos Fananos in 1995 Sycamore Conference. His paper was called FastMap. And then 3 years later, we published another paper, MetriMap, which does better in the protein domain. And this year, there's a professor in Maryland who is against, surveying this, what happens in this field. Because this mapping idea is very fancy. What does this mapping idea do is to map these fundamental data objects like protein sequences, DNA sequences, protein structures, multimedia images, and so on. Map them into points in the Euclidean space. Now, once they are mapped to points in the Euclidean space, you can use this fundamental algorithm to cluster or to classify them and so on, because they are Euclidean points. Is that clear to you? So you can use the Euclidean distance to measure their similarities or dissimilarities and then cluster them. This mapper technique is very powerful. and this represents another computing paradigm or computing method for clustering and classification. And we have fast map, we have metric, our algorithm is called a metric map, and there are several similar mapping techniques. So that's the whole idea, okay? We give the basic framework, we teach you the basic algorithm, but this algorithm has numerous applications that can be modified into different formats used in different domains, okay? So let us go back to this basic algorithm. You have 6 clusters right now. Now again, you find the 2 nearest clusters. And to find the nearest clusters, what you do is you look for nearest points coming from separate clusters, right? That's the definition of the distance between clusters. So we calculate this distance value A, distance value B, distance value C. Now look at, for example, these 2 clusters. The distance between these 2 clusters is defined as the distance between these 2 data points, okay? Why? Because the distance between this point is too large. The distance between these 2 points is still larger than the distance between these 2 points. So the distance between these 2 data points represents the distance between the 2 corresponding clusters. Any question about the definition of the distance between 2 clusters? Similarly, the distance between these 2 clusters is defined as the distance between these 2 corresponding data points. One coming from this cluster and the other coming from this cluster. Any question? So you look at these 3 distant values, A, B, C. A is smallest, so you should merge these 2 clusters together. So you merge these 2 clusters together, and then you come up with this situation in which you have only 5 clusters. You keep on doing so. This is distance A, distance B, distance C, and you calculate A, B, C. A is smallest, so A is smallest, so you merge these 2 clusters together. Now you have only 4 clusters at hand. You keep on doing so until you have only 2 clusters, okay? So we find the distance values here, distance A, distance B, and you calculate distance AB. A is smallest. You don't even bother to look at the other possible distances because they are too far. These 2 clusters are too far from each other. So your A is smallest, you should merge these 2 clusters, so you get a larger cluster because earlier these 2 clusters are nearest. Any questions so far? Then you calculate the distance between these 2 clusters, and you calculate the distance between those 2, and this is small, this is closer to each other, so you merge them together. You come up with those 2 clusters. That gives you the result. Okay. Now, as I said, all the pairwise distances between data objects should be pre-calculated, so that during the iteration you don't need to recalculate them again and again. You just look at the array and find their value. You just do the estimation. So the point is, given those 10 data points, when we group them to 2 clusters, will this give us the satisfactory results? Okay, so how do you know you should cluster into 2 clusters rather than 3 clusters? If you give, so if your case 3, you give a different result, you get a different outcome. Okay, so again, that's a parameter value that needs to be tuned, and there are a lot of papers talking about how to tune the specified the user specified parameter value. The fundamental form is like this. This is exactly published by other people. This is not invented by me. But this algorithm actually was pretty old. It was published. This algorithm was borrowed from the pattern recognition field. So a lot of database people then borrow this raw or very immature algorithm, inefficient algorithm, and then they modify this. For example, they consider the page size, memory capacity, so that they know how many data objects they should bring to the memory at one time, so that they can deal with clustering in a more efficient way. For database people, you should also consider pages or memory space, buffering, and so on, because you are dealing with databases. And then in the example, you are given only 10 points. In dealing with databases, you might have 1,000 or 1 million data objects or data points there. How to bring them into memory, how to deal with buffering, and so on. All this should be learned from CI 632 Advanced Data Management Systems. CI 631 basically teaches you data modeling stuff, how you model the data. You use a relational model. What is a relational model? Modeling basically provides a way or a tool to describe the data. So you describe the data using tables. You put this data in tables, and they are represented as tuples or records with a certain number of attributes. That's how you describe the data. That's how the relational model is used to describe the data. So that's the CI 631 is about. You learn the modeling efforts. You learn the ER diagrams. You learn the ER diagrams is another tool to describe the data, to model the data. And then you learn some, after you have the model, each model is equipped with a bunch of query languages. For example, relational model has a relational query language, has a relational algebra, relational calculus. There are formal languages. Relational system also has a SQL, which is a commercial language. You use a SQL set from where to query your database. Right now you have a data. Data models as tuples. You should use a language, or you should use some querying facilities to query the data. So SQL is one such facility, allowing you to query the relational database. So you learn all this modeling, querying stuff from CS 631, but the database management systems certainly are not that simple. You need to have a concurrency control or transaction management mechanisms to govern the execution of transactions. And each transaction might be read-only, where you have only read operations. Or each transaction might also have some update operations like write operations. How you can synchronize this access of this execution of transactions. That's basically what CI 632 is talking about. It talks about database tuning, performance, transaction management, concurrency control, query optimization. Now your query is submitted to the DBMS. How the DBMS query optimizer is trying to process a query so that the query can be presented to the user quickly and also correctly. That's the CI 631, CI 632. So the idea is that then for this data mining, we talk about these data mining algorithms. And when you incorporate these data mining algorithms into relational database management system, and you have additional considerations. Now, in that environment, instead of facing 10 points, you are facing 1 million data objects. How you are going to organize them, how you are going to bring them into memory for, when there's a clustering query submitted to the system, how you are going to optimize this data access and so on. So that's an issue in the data management. So the original idea is in the pattern recognition field, that this algorithm is invented by pattern recognition people 20 or 30 years ago. But then database people reinvent this algorithm in such a way that, this should be suitable for data management purposes. Okay, because for databases, you have a lot of data points rather than just 10. How you are going to deal with them? That's the whole idea. So there are different areas, and this, everything is you need to spend time in learning them. Okay. The next subject is a very interesting subject. That is called Outlier Discovery. For every clusters, you might have an outlier. What is an outlier? In the past, okay, Michael Jordan is considered as an outlier. Not today anymore. Michael Jordan did very poorly in this All-Stars game in the past weekend. He cannot compete with Kobe. But you have to admit that he is old. Say 20 years ago. No, it's not 20 years ago. 1988, he was the MVP of the All-Star game. At that time, he personally got 40 points. This weekend, Kobe Bryant got 31 points, which is already a good record. But about 14 years ago, Michael Jordan got 40.40 points in the All-Star game. So at that time, he was an outlier. Well, he was a genius. He's not a human being, So that's true, But Kobe now is taking over this torch. So people call Kobe Air Jordan, H-E-I-R, H-E-I-R Jordan, rather than A-I-R. The Air Jordan, right? Air Jordan means he inherits what Jordan has. So Jordan is an outlier 14 or 15 years ago. And if you look at this sports these people, their golden age is when they are 24, 25, 26, 27. I do the data mining on them. Well, I'm not the good data mining person in the NBA sports. There's Indapol, what's his name? He was IBM Watson research manager. I think 2 or 3 years ago, he gave a lot of talks about data mining MBA. He was doing that. I don't know why IBM is interested in this data mining MBA, but he gave a lot of talks about interesting things in MBA and his data mining algorithms and what patterns he found in the MBA sports. Okay, but if you look at their ages, their golden ages are around like 23, 24, 25, 26. That's their golden age. 14 years ago, Jordan was 25. Jordan now is 30, 39. So I count. So 14 years ago is 25. And Kobe now is 24. So this Kobe is Kobe Bryant's time right now. And his time is coming. Vincent Carter is that age as well. So these two people are dominating. You cannot compete with them. Jordan was he cannot. That's a fact. But still people put a lot of respect on him because he was a genius. He is a living legend. And in this area. So he's an outlier 14 years ago. So outliers are objects that are considerably dissimilar from the remainder of the data. Many of you might still be too young. I'm 40, so I always observe, try to see how Jordan is doing, and I have watched all his games when he was young. He can stay in the air for pretty long. You just cannot believe how long he can stay there, So his classical action where he goes to the basket and, everybody has already fallen to the ground and he's still on the air. And that's unbelievable. So he is different from everybody else. So he's an outlier. And why we care outliers? You have to treat outliers differently, If he is a sportsman, you have to give him different salary. so Jordan at that time, and today Jordan only wants $1 million for his salary. So he's humble. He knows that he's not the previous Jordan anymore, And Kobe has 10 million. So Kobe should be different. Okay, so outliers are treated differently. Now, for credit card applications, outliers could be fraud, so these are used to detect credit card frauds, and you have to treat them differently. You have to pay attention. If something happens that is different from regular patterns, then you have to report to your manager. Look, something happens now. Now we have to observe this, For example, some group of people are keep on using the same credit card in different places. What games they are playing? You have to pay attention at that time, So that's the data mining, why data mining is useful. They help to detect these outliers. You analyze the data. All the data are regular. They can be clustered into regular clusters. They can be put in the regular cluster. But then you observe there are 2 or 3 things that are very different from the rest. And those 2 or 3 things, you check their profile information. You see, oh, now these 2 or 3 people are doing something wrong. You have to pay observation, So a lot of people, when they do wrong things, they don't know, But then, if you are facing data mining people, you get trouble. You will soon get troubles because data mining people know how to analyze data. They pay attention on this data. They can see who is doing what. Telecom fraud detection. That's also another problem. You try to detect telecom fraud. Some people they are calling from UK to USA and so on, and the calls are very irregular. The call always occur in the morning, 3 o'clock. Or something happens, then this FBI intelligence will then pay attention. Telecom people will pay attention. That's how they know right now. They are doing it. They try to hackers. They worry about this. Uniform cancer protein. That's an outlier. Why? Because when this protein occurs and you try to put that into existing cluster, or you try to cluster these protein sequences, that protein sequence doesn't belong to any other cluster. So that protein sequence will give us trouble. So we have to pay attention on that unique protein sequence. We have to pay particular attention. So outliers have to be treated differently, either in the positive sense or in the negative sense. You have to pay attention on outliers. So a lot of algorithms developed for outlier detection. All right? So for example, you have 10 data points. All the 9 points are here, and there's an outlier there. So we have to pay attention. Okay. My philosophy is that don't be an outlier. in the real world. If you're outlier, everyone sit there and you are there. The professor is watching you. What happens on you? Something. So you are either the most distinguished, or you are or something wrong with that. Okay. So when we take exams, we are in the middle. You do not the top, not the bottom. This is a joke. Okay. Anyway, I remember when I was in the graduate school, everybody was scared by the theoretical exam, which was testing us on the knowledge of automata, Turing theorem, and so on. Very difficult exam, very, very difficult. And in particular, my graduate school, NYU, was pretty good in the theory. So they have a lot of theoretical professors. They work together to give the graduate student, to give the PhD student hard time, in the sense that they put these difficult questions. So all of us are scared by this exam. And there's one person whose name is Pankaj Agrawal. Right now, he is a Duke Distinguished Professor within only 9 years, okay? Pankaj was with us. And so we took the exam. Interesting enough, when the exam results were announced, it was not announced. It was not announced in a public way, but we all know where we are, where we stand. I got like 60 points, 60 or 62, 61. That's a pass, so I feel very happy. Most people are just like 50 something, 60 something, 7 something, 70 something. And all these are passed. If you are below 30, you fail. Pankaj Agrawal gets 100 points. So that's how we say, gosh, this person got 100 points in this exam. All the other PhD students got like 60 points or 70 points, and that's good enough, And my pragmatic exam, we also have pragmatic exam in which we are tested by compilers, operating system. I got in that particular time where I took the exam, my score is the highest. So that's another sign that perhaps means I'm very good in implementation. I don't know whether it's true or not, but I'm a good tester, So anyway, I answer the compiler question, always question pretty well, and I prepare a lot of time. But anyway, that's not a big job for this theory exam. Everybody is like 60, 50 something, 70 something. And Pankaj got 100 points. He's a father. So everybody is amazed. We all know that this is a genius. So that's a fact. So after he graduated, he joined the Duke University. And now today he's a Duke University Distinguished Professor. You can go to the cs.duke.edu. You can find Pankaj Agrawal. His name is first there because he's alphabetical order. Pankaj Agrawal is an outlier, Now, in Duke, he's not an outlier anymore because their sponsor chair, Jeff Vitter, is even better. Jeff Vitter but they are competitive. They both are very good. Jeff got PhD from Stanford. But when I was in graduate school, Pankaj was outlier in our pool. We have a lot of PhD students. We all go to the exam, and you see the outlier, and you know that he would be very good. Now he's very famous in the algorithmic field. Very famous, top researchers in the world. Jeff Vitter is another top one. These are leaders in the world. Okay, leaders in the whole world. So outliers are very, very, very good, and you can find them not very difficultly. You can find them. You can see them in the exam. In particular, in the theory exam, the professors get very difficult questions. They are very good in theory. Many of them are also leaders in the field. But then suddenly there's one student who's pop up and who can answer questions easy. And Pankaj handing this exam half hour before the end. Everybody else was sitting there. They don't want to leave there, just keep on writing, And then at the end, the professor I still remember that time, that professor was the best theory professor at NYU. He published a lot of papers. He's a leader in the field, Richard Cole, Professor Cole. But anyway, he comes to every student, he said, you have to hand in. And only Pankaj, he left the classroom early, 30 minutes early. So he can answer these questions easy. So outliers are very, very important subjects on which we have to pay attention. And Pankaj actually is among the recent NYU alumni. He's the best. He's now a Duke professor, and Duke is a top universities. Okay, it's a top university, so he's very good. So we have to agree that human being they are genius, and you see that just like Michael Jordan, who is a genius in NBA, and Kobe Bryant. These are these are too talented, you just cannot use regular ways to measure their talents. They are not human beings, regular human beings, okay? They are treated differently. That's why he deserves this, like a Kobe, he deserves this like a 10 million per year. And very few people can earn 10 million, right? But outliers are different, good outliers. There are also bad outliers. But anyway, so in our field, how we define outliers, this is one definition, distance-based outliers. Distance-based outlier with parameter value P and D is an object O in a dataset T such that at least a fraction P of the object in the dataset lie at a distance greater than the threshold D from the particular object. So outlier is here. You can find, for example, among the 100 objects, you can find at least 5 objects that are too far away from this object. For that case, then this object is defined as an outlier in this database. Okay? Or 5 objects are maybe not the right number. For example, in the database in which you have 100 objects, you can find at least 80 objects that are very far away from this particular object. So most objects are there, and this object is here. For that case, we define this object to be an outlier. This is called a distance-based outlier, okay? At least a fraction P, for example, 80% or 90%, which is a fraction. 90% of the data objects are very far away. Their distance from this object are above a threshold, meaning that they are very far away from this object. So this object then becomes an outlier because he is so far away from the majority. Majority is here, and he is a minority, he is here, okay? So how to mine these distance-based outliers if you are given a database and if you are given a distance function between these data objects? There are many algorithms. I gave you 2 algorithms here, but this index-based algorithm is basically, it's not simple. Okay, what this algorithm does is to use index-based data structure or index structure, or the so-called multidimensional data structure, such as R tree, such as KD tree. KD tree is a shorthand for k-dimensional tree, okay? These are multidimensional index structures, and they work similar to what you know about B trees. How many of you know B trees? You raise your hands, please. Yeah, you know B trees. How many of you know R trees? Raise your hands, please. R tree is a big research topic. I can give you relevant papers for R trees. Basically, R trees are multidimensional data structures to search for nearest neighbors, okay? Nearest neighbors of a input object. So for example, we use R trees, or we use KD trees, or we use any other data structures to find nearest neighbors, or to find the near neighbors of a particular object. Suppose this object has enough near neighbors. For that case, this object is not considered as an outlier. If this object has very few near neighbors, the majority is far away from this object. For that case, this object is detected as an outlier. So the point is not this algorithm itself. The point is how you run this R tree or KD tree to find the near neighbors of a particular object. And that data structure basically is beyond the scope of this class, all right? You can go to the either my 1990 paper on new techniques for best match retrieval, where we survey KD trees for finding nearest neighbors of a particular object. You can also go to my 1998 data mining and knowledge discovery paper, where you can find the references to R tree and to other kind of extensions of KD trees. And that's a big area. One of my previous PhD student, Dr. Xiong Wang, who is now a professor at the California State University, Fullerton, assistant professor there, and his PhD dissertation is dedicated to finding nearest neighbors using new data structures or index structures. He does a lot on metric map or similarity retrieval, similarity search, and so on. So you need to use a data structure to find the nearest neighbors of a particular object. Suppose this object has a lot of nearest neighbors or all near neighbors. So this object is not isolated, and therefore this object is not an outlier. On the other hand, suppose you try to find the near objects, that is, those objects that are within distance phi of this object, for example, or within distance d of this object, and you find a relatively few objects that are near neighbors of this object. For that case, this object is an outlier because only very few objects can be considered as its neighbors, and the majority of the database actually is far away from this object. For that case, it is an outlier. Nesting loop algorithm works in a different way. Nesting loop algorithm, instead of using any index structure or data structure such as R tree or KD tree or any other trees, this algorithm is just use a nested loop. For each object, you pre-calculate all the pairwise distances. So for each object, you find the nearest neighbors or near neighbors that are within distance, for example, distance d of this object. Suppose you can only find a very few near neighbors that are within distance d of this object. You know that this object is isolated, and then this is an outlier. On the other hand, for this object, you find the near neighbors that are within distance d of this object, and you almost find everybody is a near neighbor or is a neighbor of this object. For that case, he or she is not an outlier. That's a nested loop algorithm. You do this for each object, so that's a loop, right? For this object, you look at neighbors, and you check whether he's an outlier or not. And for next object, again, you check its neighbors. You see how many are neighbors of this, how many are within distance 6 of this, where 6 is a parameter value, or how many are within distance 3 of this. If there are a lot of objects that are within distance 3 of this object, then it is not an outlier because it's so close to so many people. On the other hand, if very few objects are close to this object, then he is isolated, and therefore he or she is an outlier. That's a nested loop algorithm. You do this checking for each data object. So that's a nested loop. For the first object, you find the neighbors. For the second object, you find the neighbors again. For the third, you find neighbors again. That's a loop algorithm. All right? That's how we detect outliers. Question, Tony? Louder, please.
So in a way, it's very arbitrary what it is. We can change it, and then the results will differ, right?
Absolutely right. So who will determine the distance threshold, right? Whether you should say within distance 3 or you should say within distance 5, right? But look at this, Tony. You can find that this is an algorithm, and this will eventually become a program, right? You make those become parameter values. So you can try your program. In this running, you use the 3. You can see whether results are good or bad. And then when the program gives you outcome, you see that this outcome doesn't make sense in the real world. Because you also have some knowledge when you do the clustering or outlier detection, right? For that case, 3 is not good. Let me try, say, distance 6 and use that as a distance threshold. And then run the program again. Remember, you already have a program at hand. Every time, just run it, and you give a different parameter value. All these distance thresholds, number of clusters, k, and so on, all these are user-specified parameter values. You can keep on running the programs, and you get different outcomes. And then from the outcomes, you can find a reasonable result. And then later on, you can generalize that result to other situations. That's how we do experiments. That's why every algorithm, when published, needs some experimental verification or needs some experimental validation to see how good the algorithm works and so on. Okay? Any other question you have? So that's outlier detection, and that basically concludes the whole clustering algorithm lecture. So now we have homework 3. And we also have implementation project 2. Okay. Now I will announce the due date of the implementation project 2 in the WebCT conference, WebCT conference, where you can log in and you can find the discussions or due dates for homeworks, projects, and so on, perhaps homework solutions, so on. Because I find this WebCT is very convenient and very powerful. Okay. So let me describe the homework 3. Homework 3 is to ask you to exercise the agglomerative clustering method. You are given 10 two-dimensional points as shown in the next transparency. The coordinates of the points can be found from the figure. And your job is to cluster the points into 2 clusters using the agglomerative clustering method. That's homework 3. Okay? And the input data set is like this. Now, once again, you can use ruler, straight ruler to align this. You can find the x coordinate and the y coordinate of each data point. Each data point has an integer valued x coordinate and has an integer valued y coordinate. For example, for this point, the x coordinate is 1, the y coordinate is 7. So you have the coordinates for this point. Similarly, you can have coordinates for every point, right? Then you can calculate the Euclidean distance. And then you can use this agglomerative cluster method to cluster these data points and group them into 2 clusters. That's what the homework 3 is about. Any question about homework 3? For the implementation project, I'm going to give you a very late due date for this one because you haven't handed in the implementation project 1 yet, right? So this certainly is you won't have overlapped assignments, so I'll give you enough time to do this project. What this project says is that you generate a set S of 200 points or vectors in 3-dimensional Euclidean space, and then use the Euclidean distance to measure the distance or dissimilarities between any 2 points in your data set. And then we define an outlier to be a point P where there are less than 20 points that are within distance 10 of P. So these 20 and 10 actually are parameter values. In this assignment, I give you 20, 10. But you could change that when you do your experiments. When you do your implementation, you find that 2010 might not be appropriate, so you can substitute into better values. Okay. The key idea is that you want to detect some outliers from your data point, from your data set. Okay, and print out those outliers. So what algorithm you can use? Well, you can use the nested loop algorithm, the simplest algorithm that I just explained to you. Use that algorithm to detect outliers. It's very time consuming, but it's simple, easy at this stage. If there's no outlier, your program should indicate that there's no outlier in your database. Okay? Now, but you should notice that you should provide this program because in demonstration, I may change different data sets. And for different data sets, there might be outliers and so on. For your data set that you designed, you couldn't find an outlier. But for a data set that I designed and I run your program might give you outlier. You see my point? You are developing a program. You are not just developing a subroutine that they only can run on your data set. And when other data sets are given, your program just just fails and so on. You cannot do that. When you develop program, your program should run on various data sets, not just the data set you invented. Okay? So then after you see the outliers, you should remove those outliers, and we call the resulting set S prime. Then write a program that implements the k-means clustering method to cluster the points in S prime into 5 clusters, where the number 5 again is a user-specified parameter value. Note that you should pre-calculate the pairwise distances of the points so that you do not need to recalculate the distances during clustering because all the distances are there already. You just look at them, you just plug these distance values into your calculation. So that's the implementation project 2. The purpose of this project is to let you exercise a famous clustering algorithm, namely the k-means clustering algorithm. Okay, any question about the assignments? No questions? So basically that concludes this part, and